Hi everybody, this is my solution to the ladder problem that I assigned to you guys earlier today. So again, the goal is to try and find the coefficient of friction between the ladder and the ground. This highlighted is the ladder, which is your object. It's got a length L and a mass M. And then also that there is no friction on that wall there, but there is friction on the bottom. So, all right, to start off here, it does have a mass m, so it does have weight. Weight always gets pulled about the center of mass of an object. So there we go. I'll say this is the weight of the object, mg, like that, of the ladder. There's also going to be a force. Let's see, over here, there's going to be a normal force pointing up. Right, so let's take that m, kind of throw it maybe over here, or maybe I'll throw it kind of over here. There's a normal force pointing up. So there's going to be that. Whoop, there we go. And then there's going to be a friction force. Let's say the ladder would push this way. So it'd be a friction force pointing this way. So I'll just call that FF, force of friction. And then lastly, there's going to be a force here from the wall, but that's going to be another normal force. So that's going to point like this, and I'll say F normal right there. So I'm going to start by basically saying, all right, I'm going to call this, I'm going to collapse this to a dot. So I'm going to say this is the dot that the ladder is. I'm going to start with F net equals MA. Often I would say start with torque net equals I alpha, torque net equals 0, but I think I'm going to start with F net equals MA. Let's see how far this gets me. So I got here, Fn, I'll call this Fn1, this Fn2. So I got normal force 1 pointing up. I got the weight pointing down. There's mg. I got the friction force pointing to the right. And I have the normal force pointing to the left. So and all these equal 0. So I got that the sum of the forces is equal. So F net is equal to 0. And now I got this in two directions as well. So in the vertical direction, I know that the normal force minus the weight is going to equal 0. So that basically tells me the normal force is equal to the weight. All right, there we go. And then I also know over here that I got that the normal force in the x direction, I got the, normal force 2. Normal force 2 minus the friction force is equal to is equal to 0. Getting ahead of myself here. So Fn2, the normal force 2, is equal to the force of friction. And so I got that as well. Let's not highlight it like that. Let's make it in gray. So here's relationship 1, here's relationship 2. And so, okay, that's not going to get me too far here. All right. Oh, and then also I'm trying to figure out the coefficient of friction. So let's throw in that right now. So we know that the force of friction is equal to the coefficient of static friction times the normal force. So this would be, we're talking about, this is this thing just about ready to slip, right? It's just about ready to slip, just about ready to move. And that's when we can use this. So that's what we're going to do. We're going to take that and plug that in there. And then that'll get us that the normal force 2 is equal to the force of, the coefficient of friction, and multiply by the normal force. But which normal force, right? Which normal force? Well, it'd be this. It'd be normal force 1, because that's the force that's, that's kind of causing that interaction between the friction force between the floor and the ladder. So this will be normal force 1, and I know from here, from normal force 1 here, that that is equal to mg, so I can plug that in and say that's the static friction force. So it's mu s. So this is Fn2 is equal to mu s times mg. Yeah, that's right. And replacing that for N1. And then lastly, I'll isolate mu s. So, and then, yeah, mu s like that. So lastly, the only other thing I need to worry about here, so I know M, I know L. So how can I get this coefficient of friction? Oh, and I know theta as well here is 60 degrees. So how do I get this coefficient of friction? Well, let's see. So let's now apply torque net equals I. And really all I need is Fn2. So I need this. I need to find out that. If I can get that, I can plug everything else in and I got this thing. So again, typically I'm going to use torque net equals I alpha. Or rather torque net equals 0, as the angular acceleration is 0. And so the big question is, where do you want to put your axis of rotation? And typically you put it in a place where you can simplify your... so again, you want to put it in a place so that's going to simplify your calculation. And so I would recommend, you can try different spots, but the one that's going to work the best is right here. So there's my choice of axes right there, and that means I got two torques. I got one here, that's the weight right there, and then I got one here, that's the due to the normal force. And the angle is important here as well. So let's see, I got two torques, one from the weight, so I'll call that, and let's see, using my right hand rule, the normal force 2 is going to be my positive torque. That's giving me a torque out of the page. So this will be torque from N2. And then mg is giving me a negative torque. So that's going to be negative there. So minus the torque from gravity from the weight, and that equals 0. So that basically tells me then torque of N2 is equal to the torque from gravity. So again, any torque is equal to Rf sine theta. So that basically means torque from N2, that's going to be, I'll call it R2 Fn2 sine of theta 2 is going to equal Rg mg, it's the weight, sine of theta g. Okay, so in order to get Fn2, the r vector, well, the r vector points like this, right? So here's the r vector for 2. Here's r2, and r2 is essentially the length L. So that's going to be L, and then instead of the normal, well, Fn2, that's what I'm looking for, and then sine of, what's the angle? What's theta 2? Well, I can use that law of, I got two parallel lines here, right? Two parallel lines. And I have a segment breaking up that line like that. That's what that is. So that means basically then, so here's this arrow. That means this also has to be 60 degrees here. So I can plug that in there. This is 60 equals Rg. So Rg, let's do this in a slightly different color. We'll do it like this in red. So we got that. And there's Rg. Like that, and you can basically see, well, it's acting at the center of mass, so and that's half the distance L. So this is going to be, Rg is just going to be L over 2. Let's make it all the same color here, L over 2. And then mg, that stays the same, sine of what's the angle? Well, hopefully you can see I can draw this kind of triangle, this right triangle here, and that basically tells me if this is 60 degrees, well, then that means this angle here between the r vector and the mg vector, that's going to be 30 degrees. Almost done. So this is sine of 30. Let's see. So L cancels out like that. That's nice. I'm isolating Fn2. So in isolating Fn2, that's going to give me Fn2 equals mg over 2 sine of 30 divided by sine of 60. So it's just isolating everything there. Can I just plug stuff in now? Yeah, I'm going to just plug stuff in. So I'm going to take all this. I could simplify, but I'll calculate everything at the end. So that's going to be mg over 2 times sine of 30 over sine of 60 divided by mg equals the coefficient of static friction. I can see the mass, mg cancels out all the way here. And so all I'm left with is sine of 30 divided by sine of 60 divided by 2. So let's try that. Sine of 30 divided by sine of 60 divided by 2, and I get 0.29. What can I do? Change that to, there we go. 0.29 is my coefficient of static friction. Yay! So again, I used F net equals 0, but did it in the y and x components. Then I applied torque net equals I alpha, and combined things and simplified. I also made sure to use that definition for the coefficient of static friction when something's about ready to slip, and I get 0.29. Awesome. So there you go. Hope that helped. Take care. Bye.